Welcome to my lesson here on graphing quadratic functions. This is part one of a two-part video on quadratics. The first part here is on the introduction of quadratics and some vocabulary terms and just some insight on why we might use quadratics. And the second part is actually gets into how to graph quadratic functions. I'm going to ask you to do a quick little research, a little information here on because the next example that I talk about is going to talk about the Enola Gay. The Enola Gay is a B-29 bomber that was used in World War II, and it had a crew of 12 members, and I believe Paul Tibbets was the leading crew member there. Do a little research on the Enola Gay and Mr. Tibbets there, and just kind of give yourself a little information on the background of the situation that we're going to be talking about. Why don't you go ahead and pause the video and do that, and then we will I'm going to move forward with the next example and discuss this situation here. So pause the video and do some research, then come back and let me know what you found, and I'll let you know what I found, and we'll compare. If you look at the graph here, the graph shows two lines. You have a black line and a red line. The black line is a quadratic function. It the black line here is going to represent let's see, there's one thing I didn't put on here. Let's say that thing is going to be this yellow part is kind of like the flight path of the Enola Gay. So this would be the flight path of the Enola Gay, and if we look here on the left side, in black is the quadratic equation for the black line, or the black quadratic. It says negative 16x squared plus 31,060. That is that's the equation for an object in free fall motion. That's an object that is dropped from above somewhere. It doesn't matter if it's from the top of a building or an airplane or the side of a cliff. That would be the free fall equation for that. And so 31,060, that is the moment right here in which the Enola Gay and its crew members dropped a bomb called, I believe it was called Little Boy. Okay. So it dropped the bomb called Little Boy, and they wanted Little Boy to detonate at, and you look up on the left side there, we have another equation, the red equation, y equals 1900, and that would be 1900 feet, and that's what this red line is down here at the bottom. You have this red line down here along the bottom, and that is 1900 feet. And so what the crew member and what the military had to figure out is, if they were to drop this little boy, this bomb, at 31,060 feet, how long would it take the path of the bomb to get to 1900 feet where they could detonate it, and you know, that's the question. So they needed to know how many seconds it would take in order for this to happen, and that way they knew how many seconds outside of their drop zone that they needed to release the bomb, in order for it to explode where they needed it to explode. So if we look here, where the quadratic and the red line intersect is going to be how many seconds? This number right here is 40 seconds. This number right here is 45 seconds. So the number we're looking at, you can kind of see the mark there for 42.5, which the number that we're looking at is just above that, 43 seconds. That's how long it's going to take. And so they needed to, this is one use for a quadratic equation. Hopefully it's a use that we never have to use again, because when you drop bombs, usually things get destroyed and people get hurt, or even worse, they perish. So, although I think as an American, I think you understand the importance of the Enola Gay and the little boy, and the reason why we needed to stop World War II, and this was part of that ending process for us, I guess. So if we look here, this is one use for a quadratic equation. Many, many more uses. A lot of times you guys find it hard to understand why we use mathematics in real life. Sometimes, you think that you're never going to use it, and if we look here, I'm going to venture to say that those gentlemen flying the Enola Gay, found it quite handy to know a little mathematics, to know when they needed to, let go of the bomb and to try to save America, I guess. If we look here, so that's one example here. Let's go to the next slide. I'm going to show you a different view of the same graph, just a different view of it. And we were only concerned from the y-axis down, because that's the free fall of the object. The object doesn't start here at the ground and then come up and then come down. So that's the reason why I didn't show you the left part of the graph here. Notice, I'll go back. Notice I didn't show you the left part of the graph, because in a real life situation, this part of the graph, the left part of the graph, didn't actually happen. I know at some point the object had to go up in the air, but it didn't go up in the air along this path. It went up in the air along a different path. And but the free falling is what we were looking at. But I wanted to expand this out so you could see what a quadratic looked like. It kind of looks like a that black line, we're going to call it a parabola. I'm going to give you the definition here in a minute. And the definition of it is a U-shaped graph. But the thing is, if we look at it, it's always going, bottom right corner of the screen, it's always going to continue on and on forever. Where I think sometimes you will go straight up in the air, but a parabola kind of points outwards a little bit. It'll point outwards a little bit, and you can notice that a lot on this one. You can notice that a lot on the black line that I have there. So this is kind of an introduction here, a quick understanding of why we use quadratics. That's one example of why we use a quadratic. A quadratic function, standard form. I should have this memorized, because we're going to need to know sometimes what A, B, and C are. And actually, you do need to have it memorized, because when you go to graph, you need to know A and B. You need to use A and B to find the vertex of the graph. So if we look there, standard form is y equals ax squared plus bx plus c. Your first definition is parabola. It'll be the U-shaped graph of a quadratic function. I've already showed you two examples of that. If you want to go ahead and pause the video here, we'll pause the video here while you write down the definitions, and then I can explain those in one moment for you and give you an example. The vertex is going to be the lowest point on a parabola that opens up, or the highest point on a parabola that opens down. And the axis of symmetry is the vertical line passing through the vertex of a parabola, creating two symmetric parts, or mirror images of each other. I think the next page I have here shows you those. Okay, if we look here, here's the standard form. And here's the equation that we're working with. Y equals x squared plus 2x minus 3. Or if you need to think about it here as c is negative 3. I mean, if you see this here, because the standard form says it's supposed to be a plus sign. So therefore, if it's a minus sign, c is going to be negative 3. And that goes the same with b and a. If there's a minus sign there or a negative sign, A or B will also be negative. In this case, A and B are both positive. So if we look here, I have labeled A, B, and C. A is the invisible 1, B is a positive 2, and C is the negative 3. So that's the part that we have. And I want to look over here and talk about some definitions. What you see here on the red graph here is going to be a parabola. It's a quadratic function, which is y equals x squared plus 2x minus 3. So the graph there is called a parabola. What are some other things here? The axis of symmetry. The axis of symmetry is right here. It's the green line, the green vertical line, and the equation for that is x equals negative 1, because as you know from graphing lines before, x is equal to negative 1 should be a vertical line that crosses the x-axis at negative 1, and that's what the axis of symmetry does. So now if you look on the left side of the axis of symmetry and you look on the right side of the axis of symmetry, imagine if we were to take the graph and fold it in half along the axis of symmetry. The left side of the graph and the right side of the graph are going to fall on top of each other. And we can look here. The distance from these points are the same. They are 3 away from the axis of symmetry. And the distance from these 2 points are the same. This one is 2 away, and this one is also 2 away. And the distance here is the same. That one is 1 away, and that one is 1 away. And that's not just the points that we can see there. If we were to draw the line here, this point is the same distance away as this point from the axis of symmetry. And I know that might not look exactly correct because I hand drew the parabola in there. But if we were to use some sort of computer device, it would be exact, and you would see that distance is equal. So that's the axis of symmetry there. If you look, we are one other vocabulary term we have to identify. That last vocabulary term is called the vertex. In this case, since the graph opens up, since the parabola opens up, the vertex is going to be the lowest point, or the minimum point, and it is right there. That's going to be the vertex. And you notice the vertex lies on the axis of symmetry. So if you know the ordered pair to the vertex, which this ordered pair is going to be negative 1, 1, 2, 3, 4, negative 4, then you can find the equation for the axis of symmetry because you just say x is equal to -1. Let's look at another type of parabola here. When we have the parabola that opens down like that, when it opens down, there's the quadratic formula, or the quadratic function there. Y equals -x squared plus 2x plus 4. You notice A is -1, B is your +2, and C is a +4, and I have that written there. The parabola is the blue line there. A couple things to notice when you graph this right here. It is not it is not a V. Okay, the parabola is not a V. And when you graph this as a U shape, it does not come to a single point. What this is actually doing here is that it comes, you don't see a single point up here at the top of the graph. There's not one single point. It's kind of just a smooth rounding at the top, and it barely touches the vertex. I mean, it rounds through, touches the vertex, and then it keeps going, keeps on going. You could probably say it just keeps on trucking after it goes through the vertex. That's a good term for it. So remember, it's a smooth rounding at the vertex when you graph a parabola. It does not come to a single point. And let's look here. What is the axis of symmetry? The axis of symmetry is a vertical line that crosses through the vertex so that it creates a mirror image on both sides. So there's the axis of symmetry. The equation, x equals 1. So it's a vertical line that's going to cross the x-axis at 1. And remember, creates a mirror image. That point is 3 away. This point here is also 3 blocks away. This is 2 blocks away. And this point is 2 blocks away. And 1 block away. And 1 block away. So the axis of symmetry creates a mirror image on both sides. And this is an important concept because when we go to graph, we're going to use that concept to save you a little bit of time. What is the vertex here? The vertex is going to be that point right there. We know that point is going to have an x value of 1 and a y value of 1, 2, 3, 4, 5. So there's the vertex. The vertex is at 1, 5. So those are some uses of your vocabulary terms for parabola, which is just the graph, the blue graph there, the U-shaped graph, axis of symmetry, and vertex. Here's a couple notes. This says if A is positive, the graph opens upward. See example 1. And if A is negative, the graph opens downward. See example 2. Well, look at this. I'll go back to the last slide for you here in one moment so you can write that down. But let's look at A. A is +1, so the graph is opening upwards. Let's look at A here. A is -1, so the graph is opening downwards. The value there, this says -1. The number 1 there doesn't determine whether it opens up or down. It's the positive and negative sign that determines whether the graph opens up and down. So that's what we're looking for there. When you go to graph this, you should see, hey, A is negative here. The graph is going to open down. Um, let's look at C down here at the very bottom. It says C is the y-intercept. And if you look in the graph right here, positive 4 is C. C is 4. Is that the y-intercept? Well, 1, 2, 3, 4. Right there would be the y-intercept, and that is C. Let's look here at the previous example. Right there, C, negative 3. Negative 3. Right here would be the y-intercept. Is it at negative 3? 1, 2, 3 down. Yes, it is at negative 3, so that is the y-intercept. So those are some things that you'll want to pay attention to when you go to graph quadratics. It's just make sure your y-intercept is the y-intercept, and if A is positive, it opens up. If A is negative, it opens down. And then there's some other things that you need to pay attention to with A. We're going to get to that when we graph. We'll talk about it. Here's that last slide for you again. That way you can go ahead and write that stuff down. That's all I have for your introduction into graphing quadratic functions or quadratic equations. So we will we're going to have the next lesson for actually how to graph. We're going to have that up in one moment. So if you as soon as you're done here, you can go ahead and take a break and then watch the next one. If you have any questions, let me know.